The circuit breaker is primarily intended to protect the wire and prevent damage due to excessive current flow. The circuit breaker rating should be based on the full load current or flaw of the motor. For a 6.0 amp motor, a 30 amp circuit breaker is appropriate. A 70 amp breaker is too large and would not provide adequate protection for the number 10 American wire gauge wire. Motors draw higher current during start-up than during normal operation. The circuit breaker is rated to carry the start-up current momentarily without tripping. However, the breaker does not need to be rated specifically for start-up current as long as it is sized appropriately for the motor's FLA. Number 10 American wire gauge THHN wire is sufficient for a 6.0 amp motor at 480 volts. The voltage drop at 30 amps is negligible. A 30 amp circuit breaker is appropriate for 6.0 amp motor on number 10 American wire gauge THHN wire. A 70 amp breaker is too large and would not provide adequate protection for the wire. The circuit breaker does not need to be rated specifically for start-up current. When selecting a circuit breaker for motor protection, several factors must be considered to ensure both safety and optimal performance. Firstly, determine the motor's full load amps, or FLA, from the motor's nameplate. This value is crucial as it represents the steady-state current the motor draws when operating at its rated load. Secondly, refer to the National Electrical Code, or NEC, Table 430.52, which provides guidance on the maximum allowable overcurrent protection for motor circuits. This table typically allows for an instantaneous trip circuit breaker to be sized up to 800% of the motor's FLA, but this is primarily for allowing the motor to start without nuisance tripping. Thirdly, consider the conductor ampacity. The circuit conductors must be sized to carry at least 125% of the motor's FLA, as specified in NEC 430.22. This ensures that the conductors can handle the continuous load without overheating. Fourthly, select a circuit breaker that provides both short circuit and overload protection. Short circuit protection is intended to quickly interrupt high fault currents, while overload protection is designed to protect the motor and conductors from prolonged overcurrent conditions. Fifthly, coordinate the circuit breaker with motor's thermal overload protection. Motors are typically equipped with thermal overload relays that protect against sustained overcurrent conditions that could damage the motor. The circuit breaker should be sized to allow the overload relay to trip before the breaker does, ensuring that the motor is protected from damage. Sixthly, account for voltage drop. Excessive voltage drop can cause the motor to run inefficiently and can even damage the motor. Ensure that the circuit conductors are adequately sized to minimize voltage drop, especially for long circuit runs. Seventhly, consider the type of motor and its starting characteristics. Motors with high inrush currents, such as across-the-line starters, may require larger circuit breakers or time delay fuses to prevent nuisance tripping during startup. Eighthly, ensure that the circuit breaker is properly labeled and identified. Clearly label the circuit breaker with the motor's name and function to facilitate maintenance and troubleshooting. Ninthly, consult with a qualified electrical engineer or electrician to ensure that the circuit breaker is properly sized and installed in accordance with all applicable codes and standards. Improperly sized or installed circuit breakers can pose a significant safety hazard and can damage equipment. Tenthly, periodically inspect and test the circuit breaker to ensure that it is functioning properly. Circuit breakers can degrade over time due to environmental factors or repeated tripping. Regular inspection and testing can help identify potential problems before they lead to equipment failure or safety hazards. In the case of a 6.0 amp motor, a 30 amp circuit breaker may be suitable, but it is essential to verify that the size complies with the NEC and the motor manufacturer's recommendations. A 70 amp breaker is likely too large and would not provide adequate protection for the conductors, potentially leading to overheating and fire hazards. Always prioritize safety and compliance with applicable codes and standards when selecting and installing circuit breakers for motor protection. Remember to consult the motor's nameplate for the full load amps. Check NEC Table 430.52 for maximum overcurrent protection. Ensure conductors are sized at 125% of the FLA per NEC 430.22. Coordinate the breaker with the motor's thermal overload protection. Minimize voltage drop by properly sizing conductors. Consider the motor type and starting characteristics. Label the breaker clearly for easy identification. Consult a qualified electrician for proper sizing and installation. Inspect and test the breaker regularly for optimal performance. Selecting the correct circuit breaker involves a detailed understanding of electrical codes, motor characteristics, and safety considerations. By following these guidelines, you can ensure that your motor is adequately protected against overcurrent conditions while maintaining a safe and reliable electrical system. The importance of correctly sizing a circuit breaker for motor protection cannot be overstated. An undersized breaker will trip frequently, causing unnecessary downtime and potentially damaging the motor due to repeated starting attempts. An oversized breaker, on the other hand, will not provide adequate protection against overloads and short circuits, increasing the risk of conductor damage, equipment failure, and even fire. To further elaborate on the selection process, consider the different types of circuit breakers available. Firstly, standard thermal magnetic circuit breakers are the most common type and are suitable for general-purpose applications. They use a thermal element to provide overload protection and a magnetic element to provide short-circuit protection. Secondly, instantaneous strip circuit breakers, also known as motor circuit protectors, are specifically designed for motor circuits. They provide very fast short-circuit protection but do not offer overload protection. These breakers must be used in conjunction with a separate overload relay. Thirdly, inverse time circuit breakers are designed to trip faster as the current increases. This characteristic makes them well suited for protecting motors with high inrush currents. Fourthly, electronic trip circuit breakers offer advanced features such as adjustable trip settings, metering, and communication capabilities. These breakers are often used in critical applications where precise control and monitoring are required. When selecting a circuit breaker, it is also important to consider its interrupting rating, which is the maximum fault current that the breaker can safely interrupt. The interrupting rating must be higher than the available fault current at the breaker's location to prevent the breaker from failing during a short circuit event. Another important consideration is the ambient temperature in which the circuit breaker will be operating. Circuit breakers are typically rated for a specific ambient temperature, and their performance can be affected by extreme temperatures. If the breaker will be installed in a high-temperature environment, it may be necessary to dare at its current carrying capacity. In addition to the NEC, other standards and guidelines may apply to the selection and installation of circuit breakers for motor protection. For example, the National Electrical Manufacturers Association, or NEMA, publishes standards for motor control equipment, including circuit breakers. The Institute of Electrical and Electronics Engineers, or IEE, also publishes standards related to electrical safety and equipment protection. Finally, it is important to remember that electrical work can be dangerous and only qualified personnel should perform it. Always to energize the circuit before working on electrical equipment, and follow all applicable safety procedures. If you are not comfortable working with electricity, consult a qualified electrician. Properly sizing a circuit breaker for motor protection is a critical task that requires careful consideration of various factors. By following the guidelines outlined above and consulting with qualified professionals, you can ensure that your motor is adequately protected against overcurrent conditions, while maintaining a safe and reliable electrical system. When dealing with motor protection, several additional factors warrant attention to ensure comprehensive safety and optimal performance. Firstly, harmonic currents can significantly impact motor performance and protective device operation. Harmonic currents are non-sinusoidal currents that can cause overheating, voltage distortion, and increased losses in motors and transformers. To mitigate the effects of harmonic currents, consider using harmonic filters or reactors to reduce the harmonic content in the electrical system. Secondly, ground fault protection is essential for preventing electrical shock hazards and equipment damage. Ground faults occur when current flows through an unintended path to ground, such as through a person or equipment enclosure. Ground fault circuit interrupters, or GFCIs, and ground fault relays can detect these faults and quickly interrupt the circuit, minimizing the risk of injury or damage. Thirdly, surge protection is important for protecting motors and other electrical equipment from transient voltage surges caused by lightning strikes, switching operations, or other disturbances. Surge protective devices, or SPDs, can divert these surges to ground, preventing them from damaging sensitive equipment. Fourthly, motor starters play a crucial role in controlling the starting and stopping of motors, as well as providing overload protection. There are several types of motor starters available, including across-the-line starters, reduced voltage starters, and variable frequency drives, or VFDs. The choice of motor starter depends on the motor size, application requirements, and the characteristics of the electrical system. Fifthly, motor enclosures are designed to protect motors from environmental factors such as dust, moisture, and corrosive substances. The type of enclosure required depends on the application environment. NEMA standards define different enclosure types, each with specific protection characteristics. Sixthly, motor maintenance is essential for ensuring long-term reliability and performance. Regular maintenance tasks include inspecting motor windings, bearings, and connections, as well as lubricating moving parts and cleaning the motor enclosure. Seventhly, energy efficiency is an important consideration when selecting and operating motors. High-efficiency motors can significantly reduce energy consumption and operating costs. Consider using premium efficiency motors and implementing energy-saving measures such as variable speed drives to optimize motor performance. Eighthly, motor monitoring systems can provide valuable data on motor performance, including current, voltage, temperature, and vibration. This data can be used to detect potential problems early and prevent costly downtime. Ninthly, coordination studies are essential for ensuring that protected devices in an electrical system are properly coordinated to minimize downtime and prevent cascading failures. Coordination studies involve analyzing the time current characteristics of different protective devices to ensure that the device closest to the fault trips first, isolating the fault and minimizing the impact on the rest of the system. Tenthly, safety training is crucial for all personnel who work on or around electrical equipment. Training should cover topics such as electrical hazards, safe work practices, and the proper use of personal protective equipment. Implementing these additional measures can further enhance the safety and reliability of motor protection systems. Always consult with qualified professionals and follow applicable codes and standards when designing, installing, and maintaining electrical systems. Remember to consider harmonic currents and use harmonic filters or reactors. Implement ground fault protection with GFCIs or ground fault relays. Utilize surge protection devices to protect against voltage surges. Choose the appropriate motor starter for the application. Select the correct motor enclosure for the environment. Perform regular motor maintenance for long-term reliability. Consider energy efficiency by using premium efficiency motors. Implement motor monitoring systems for performance data. Conduct coordination studies for proper protective device coordination. Provide safety training for all personnel working with electrical equipment. Ensuring comprehensive motor protection involves addressing these factors in addition to properly sizing circuit breakers.